Okay, so this is 6.1, and we are going to talk about velocity and net change. So the good thing is a lot of the concepts that we have previously learned are going to apply in this section. So it shouldn't be too difficult. We're just going to expand upon our knowledge a little bit. So the first thing I want you to think about is you're driving along the highway in a straight line. Your position relative to your reference point or your origin changes in relation to your time changing, okay? And so we call that displacement. So we have already been talking about how okay, how our position and velocity and acceleration are all related. So we are going to add on to that just a bit, all right? So as you remember, the derivative of your position function is your velocity, and the absolute value of your velocity is your speed. The displacement is how far you travel from the starting point to the ending point. So we use the change in the ending point minus the change in position of the starting point to figure that part out, okay? So let's go ahead and do a real example. Okay, so sorry I keep focusing you. All right, so we have a cyclist and they are pedaling along a straight road, and they've given us the velocity here, and they want to have us graph the velocity function over the interval from 0 to 3 and determining when the cyclist is moving in a positive direction. Okay, so what I did for this is I just popped this equation into Desmos using X instead. You can also do that in your graphing calculator. And what I noticed was it gave me a function. And what I want to draw your attention to is I could factor out a 2. And then if I were to factor this, that would give me t minus 3 and t minus 1. So a time of 1 and a time of 3. And what I noticed was between 1 and 3, the velocity was negative because it was below my x-axis, okay? So this tells me that from 0 to 1, the velocity is positive because it was above the x-axis. So therefore, the cyclist is moving in a positive direction, cyclist. Okay. And then from 1 to 3, the velocity was negative because it was below the x-axis. So therefore, the cyclist is moving in the negative direction. Okay, so now what we're going to do is we are actually going to find the displacement. So they've given us 3 different intervals where they want us to find the displacement. So if we're thinking about this first one right here, what that essentially is asking me to do is to find the position at 1 and find the position at 0, and we're going to subtract them, okay, to find the displacement. So what I can do is I'm going to rewrite that. Okay, so I'm going to integrate my velocity function, and then I'm going to evaluate that on the interval of 0, 1. Okay, so what this is going to look like, we're going to go ahead and substitute in our velocity function. Okay. All right, so now I'm just going to integrate this. So okay, so I always like to write out before I simplify just to make sure I don't make any mistakes. So I'm going to have 2/3 t cubed minus 4t squared plus 6t, and I'm going to evaluate that at 1, 0. Okay, so when I plug in 0, it's all going to go away because everything has a t in it. So I essentially just need to plug in the 1. And if I do that, I'm going to get 8/3. And we're in miles. So the displacement from 0 to 1 is 8/3 of a mile. Okay. All right. Now let's do 1 to 3. So since I have already integrated, I can just simply use the same integration. I don't have to redo it because it's not, that part's not going to change. So from 1 to 3. Oh, I forgot this part. Oop. 2/3. Okay, so if I type all that into my calculator, making sure to put a second set of parentheses or brackets around this second part, I'm going to get negative 8/3. Okay, so what I want you to think about now is we found how far we traveled on the interval from 0 to 1. We found how far we traveled on the interval of 1 to 3. So essentially what you could think about, if I went from 0 to 1, and that was 8/3 of a mile, and I went from 1 to 3, and that was negative 8/3 of a mile. Essentially, if I was then looking at just 0 to 3, I would add these two pieces together. And if I add the two pieces together, I'm going to get 0 miles. So what does that mean? That means the cyclist traveled down the road and then it came back. Okay. All right. So the next question wants us to find the actual distance traveled. So essentially, what we're going to think about is the fact that the cyclist on the interval from 0 to 1, we found that they traveled 8/3 of a mile. And then on the interval from 1 to 3, they traveled 8/3 of a mile back. So all I have to do now is add those two together to get my total distance. And that's 16/3 of a mile. Okay. Okay, so as we've been doing, we know that the position function can be found from our velocity, and we find that by performing the integration, okay? Now, your initial position, if it is not at 0, you're going to need to take that into account, and we're going to take that into account later. But it's just something to keep in mind. If they don't start at 0, like if they start 5 miles west or something, you're going to have to take that into account afterwards to make sure that you account for that. That was not a very good way to say that. Okay, so let's do an example. I'm going to show you what I mean. Okay. So we have a block that is hanging from a massless spring at the origin. So S equals 0. At time equals 0, the block is pulled downward 1/4 of a meter to its initial position. So its initial position is -1/4, and then we release it. The velocity in meters per second is given by the following formula. Assume the upward direction is positive. Find the position of the block for t is greater than or equal to 0. Okay, so what they told me was the velocity is 1/4 sine t, right? So what we're going to do is we're going to integrate that to find our position function. So I know that in order to get sine from the derivative, I had to have cosine, but the derivative of cosine is negative sine. So I know I'm going to need a negative. So if I integrate this, I'm going to get -1/4 cosine t plus c. Okay, so we can solve for c by plugging in 0 for t and setting it equal to -1/4. Okay, so -1/4 equals -1/4 cosine of 0. Well, what's cosine of 0? Cosine of 0 is just 1. All right, so then essentially, if I add 1/4, I get a c value of 0. Okay, so that is telling me that my position function is just going to be -1/4 cosine of t. Okay. All right, so now the next part wants us to graph this on the interval from 0 to 3 pi. Okay, so 0 to 3 pi. Okay, so what I want to think about with this is we know initially the block is down at -1/4. And this makes sense because if I were to plug in 0, it's kind of very similar to what we, exactly similar to what we just did. The cosine of 0 is 1, okay? So I'm just going to end up with -1/4, which is why we're starting here, -1/4. All right, so then the next point that I have on my graph is pi over 2. So -1/4 times the cosine of pi over 2. Okay, so what is cosine at pi over 2? It is 0. Okay, so this is going to end up giving me 0. Okay, now we're going to do pi. Okay, so at pi, cosine is -1. So if we have -1/4 times -1, that's going to give me a +1/4. All right, so you probably are seeing the pattern now. It's just going to cycle through that like so, traveling up and down between -1/4 and +1/4 and stopping at 0 in between. All right. Okay. The next question, we're still talking about the block, is asking us when is the block going to move through the origin for the first time. So since we have already done the graph, we can also see that from the graph. Where is that happening? Where is it hitting 0? But let's go ahead and solve for it as well. So when we're going through the origin, that's telling me that my position function is equal to 0. So we say -1/4 cosine of time equals 0. Okay, so we could divide by -1/4, but that's not really going to change anything. So then this is asking me, where is cosine equal to 0? And the answer is pi over 2. Okay. All right, I think we got one more like this. Yep, one more block question. Okay, so this is a good one. This is asking us, when is the block reaching the highest point for the first time, and what's its position at that time, and when does it reach the lowest point? Okay, so our highest point on our graph was a positive 1/4, and the lowest point was negative 1/4. Okay, so the highest was positive 1/4, and the lowest is negative 1/4. Okay, so what we're essentially going to do is we're going to say 1/4 equals negative 1/4 cosine of t, and we're going to solve for that time. So I'm going to divide by negative 1/4, which is going to end up giving me negative 1 on this side. And where is cosine equal to negative 1? And the answer is at pi. Now the lowest point, it does start out at negative 1/4, but we want to figure out when it returns to negative 1/4. So in this case, I'm going to set it up the same way, except this time it's equal to negative 1/4. So we again are dividing. I'm getting a positive 1. So where is cosine equal to positive 1 and not 0? But we want what happens after that, and the answer is 2 pi. Okay? All right. Okay. So next question, let's switch it up. It wants us to graph the velocity function on the interval and determine when the object is moving in the positive direction and when it's moving in the negative direction. Okay. So what I did for this one is I plugged this into Desmos. And what I saw was a graph, and it never went below the x-axis. So what does that tell me? It tells me that on this interval, it is always positive. It's not moving in the negative direction. Okay. Okay, so now we need to find our position function. So this one's going to be a little yucky to integrate, but we can do it. Okay, so let me see. The first thing that I'm going to do is I'm going to write this as 20 t plus 1 to the negative 1/2 dt. Okay, so we need to integrate this, right? And what I'm going to do to make my life a little bit easier is I'm going to take 20 out in front of my integral symbol. So then we're going to end up with 20 t plus 1 to the negative 1/2 dt. Okay, so we are in essence going to need to do u substitution. Okay, so we would say that u equals t plus 1. The derivative of u would be 1 dt. And then u to the negative 1/2, if I'm going to integrate that, what we essentially are going to do is add 1 to the negative 1/2. So that is going to give me a positive 1/2. And since there was nothing left over, I know I'm going to need to multiply by the 2 so that that would go away when I then take the derivative. So 1/2 times 2 gives me 1, and that goes away. And if I subtract 1 from there, I get -1/2. So that's my check to make sure I did it correctly. So what does that tell me? That tells me I have 20 on the outside from there. And then we have 2u, t plus 1, to the positive 1/2. All right, and then we'd have to multiply that by the whatever the value was here, but since it's 1, that's not going to matter. Okay. Okay, so what I can do now is I can multiply the 2 times the 20, and of course, don't forget your c. So we're going to end up with 40 t plus 1 to the 1/2 plus c. Okay, so now what can we do? We can solve this for c. And how can we do that? Well, if we look at this initial condition here, that's telling me when I substitute in 0, I get 4. Okay, so let's do that. So 40 times 0 plus 1 to the 1/2 plus c is equal to 4. Okay, so what is this going to give me? 0 plus 1 is 1 to the 1/2 is 1. 40 times 1 is 40 plus c equals 4. Okay, so c equals -36. All right, so let's just rewrite our position function. And that's it. Okay. All right. I think that was it for this example. Yeah, we got one more different example. Okay. So we have a skydiver. Do any of you want to skydive? My sister's done it a bunch of times, but I am not that brave. Okay, so what the skydiver does. So we have a helicopter. See if I can draw it. Does that look like a helicopter? No, that does not look like a helicopter. Don't they have like, I don't know. This is like one of those military ones. I think my husband called it a Chinook or something. Okay, whatever. That's probably not one that they jump out of. Whatever. Okay, so the skydiver jumps out. He's falling 80 meters per second for 19 seconds. So from the first 0 to 19 seconds, he is falling 80 meters per second. And then he opens his parachute. And so the parachute opening causes him to decrease linearly 6 meters per second over a 2-second period. So they already found the equation for us. They gave it to us. That was very nice. And then he is, then his velocity remains constant as he travels to the ground from 21 to 40 seconds, okay? We want to figure out his altitude. All right, so what we're going to do is we are going to integrate each piece and evaluate it at each specific time respective to that function, okay? So 80, when we integrate that, is only going to be evaluated from 0 to 19. This is going to be evaluated from 19 to 21, okay? So I'm going to write it down here just because I have more room down here to write. Okay, so let's see. Okay, so just to recap, 80, 0 to 19, this 19 to 21, 6, 21 to 40. Okay, so let's go ahead and integrate. So this first one is going to be 80t, and we're going to evaluate that at 19 and 0. This one is going to be 783t minus 37 times 1/2 t squared, and we're evaluating that between 21 and 19. And then this is going to be 6t, and we're evaluating that at 40 and 21. Okay, so let's plug all this in. Okay, so 80 times 19 and minus 80 times 0 is going to be 1520. Uh, 21. All right, this, when I plugged it in, I got 86. Oh, sorry, didn't realize the thing was not visible. Okay, and that should be a minus. Okay, and when I did that, I got 114. Okay, and so then I'm going to add all that together. I'm going to get 1,720 and meters. Okay. All right, so just got a little bit more. Okay, so as you know, velocity and acceleration, they have the same sort of relationship that velocity and the position function have, okay? So let's do an example. We have an artillery shell that's fired directly upward with an initial velocity of 300 meters per second. At a point 30 meters above the ground, assume that only the force of gravity acts on the shell and produces an acceleration of 9.8 meters per second squared. Find the velocity of the shell for t is greater than or equal to 0. Okay, so gravity pushes things down, so we're going to need a negative for this acceleration. Okay, and so all we have to do now is we need to integrate this. So the velocity is going to equal to negative 9.8x plus c, and it's giving me an initial velocity of 300 meters per second. So what that is telling me at v equals 0, the answer is 300 meters per second. So if I were to substitute in 0, it's going to equal 300 meters per second. So it's essentially giving me my c. Okay. Okay, now the next example wants us to still work with this same problem, but we want to find the position function. Okay, so see how I said this was similar to what we've been doing? We're going to add on to it in just a second. Okay, so now we are finding the position. So the velocity that we just found was negative 9.8x plus 300. So we're going to integrate this. Okay, so we're going to get negative 9.8 times 1/2 x squared plus 300x plus c. Okay, so we can simplify, and that's going to give me negative 4.9x squared plus 300x plus c. Okay, so they told me that we are starting 30 meters above the ground. Okay, so essentially that tells me at s equals 0, the answer is 30. Okay, so I could plug that in, but I know that that those both are going to go away. And so I'm going to end up with C equals 30. And that one is done. Okay. All right, so here's another example. And I think maybe you should try this one. Okay, so go ahead and pause the video and try this one. All right, so what we're going to do now is we are going to take the concepts that we learned with acceleration, velocity, and position and relate that to things that are not simply acceleration, velocity, and position. Okay, so because we can talk about other things, not just that stuff. All right, so this just is giving us like what we've been doing and same sort of thing, but just we're, you know, calling it different things now. So instead of velocity, we're going to say rate of change. Instead of displacement, we're going to say net change. Instead of future position, we're going to say future value. Okay, so nothing is really going to change except the fact that we are no longer doing just velocity and position. Okay, so let me show you what I mean. All right, so we have the owners of an oil reserve are extracting oil at time t equals 0. It wants us to find how much oil is extracted in the first 10 years. Okay, so what we need to do is first, my equation I'm gonna FOIL this and then I'm gonna factor this, okay? Because it's gonna be too messy to integrate otherwise. So I'm gonna get and I should write this. We're gonna be going from 0 to 10 because I want the first 10 years, okay? Now let's go ahead and do this. Okay. Oh, yeah, okay. All right, so now we can integrate. So I'm gonna end up with 4,800 t times 1/3 t to the third minus 240 times 1/4 t to the fourth. Better, that's all sloppy. Okay, and we're evaluating that between 0 and 10. Okay, so let me just clean this up just a little bit. So we're going to get 1,600 t cubed minus 60 t to the fourth plus 3/5 t to the fifth. And we're evaluating that at 10 and 0. Okay, so let's sub in. Let me actually write this on the side over here. So okay, so 0 is not really that fun because it's just all going to go away, but we're going to write it down anyway. All right, so what are we getting? Let me make sure I got this right. 1, 2, 3. Yeah. Yeah, okay, good. All right, and this is in millions of barrels, so millions. It's a lot of barrels. Okay. The next one wants us to find how much oil is extracted after 40 years. Okay. So essentially, I'm going to be using the same equation. But instead of evaluating it at 10 and 0, I'm going to have 40 and 0. And that is going to give me 10, what would I say, million? Okay. All right, now this next one is a good one. Okay, so for this next one, it just wants year 40. Okay, so what we're going to do is we're actually going to evaluate this at 40 and 39. Because then we get what happened in year 40. Okay, so if I substitute in 40, oh, I'm writing this all wrong. You feel like that your brain goes faster than your hand can keep up with? Okay. And then I substitute in 39, and this is what I got. And so I'm going to subtract them, and I'm going to get millions of barrels. Okay. All right, let's do another different example. Okay, so we have some prairie dogs. And initially there are 55 of the prairie dogs. They're growing at a rate of 20 minus t over 5. And that's prairie dogs per month. What's the population 6 months later? Okay, so we are going to integrate this function. On the interval of 0 to 6 because it says 6 months later. Okay. And that is going to give me 116.4. Okay, now we're not cutting dogs in half. That's violent. Don't do that. So you're going to round this down. Okay. So we're going to say 116. Now, how many did we start with though? We started with 55. So 55 original. We're going to add that together and we're going to get 171 prairie dogs. Am I even spelling this right? Prairie dogs? Yeah, it looks weird. Okay. Now the next question just wants us to find a generic equation that would work for all the prairie dogs. Okay. So what we essentially are going to do, we already did the hard part. We got this. Okay. Initially, we had how many prairie dogs? 55, right? So essentially, if I substitute in 0 for t, it equals 55. Now, if I substitute in 0 for t, this is going to go away, this is going to go away, and essentially c is going to be 55. So we're going to say 20t minus 1/10. Okay. All right, there's one more example on this. I want you to try this and then check online to see if you got it correct. All right?